Students, today we will start your next chapter in physics, that is gravitation. Let's start. This chapter contains 4 parts: Kepler's law of gravitation, universal law of gravitation, thrust and pressure, Archimedes principle and buoyancy. But the last 2 topics, okay, thrust and pressure and Archimedes principle and buoyancy, this has been deleted by the CBSE. Okay, these are the deleted portions. So only portions that we have to cover is Kepler's law of gravitation and universal law of gravitation. Okay, only these topics we will cover. So let's start.
Autumn to winter, winter into spring, spring into summer, summer into fall. So rolls the changing year, and so we change. Motion so swift, we know not that we move. The changes in seasons have inspired a lot of poets. But scientifically speaking, do you know how the phenomenon of changes in the seasons can be explained? It's all connected to planetary motion. Ptolemy showed the world a geocentric solar system, which was centered on the Earth with the Moon, the Sun, and 5 planets revolving around the Earth in perfect circular orbits. Then came Nicolaus Copernicus, who presented a heliocentric solar system. This model showed the Sun at the center of the solar system, with planets revolving around the Sun in circular orbits. However, neither of these models could explain the variations in seasons or the lengths of days over the year.
Okay, what we saw that different theories that have come up, but no one explains that how do the seasons come and go, okay?
Finally, Johannes Kepler, a German mathematician, astronomer, and astrologer, in his laws of planetary motion, explained that planets revolve around the Sun in elliptical orbits, resulting in the change in distance from the Sun at various times of the year.
Okay, Kepler gave the planetary motion, which told about all the different seasons, how do they come and go, and how the planetary motion occurs.
Kepler's laws helped explain, among other things, the reason for changing seasons on Earth. In this lesson, you will learn about Kepler's laws of planetary motion.
What are the topics that we will cover in this module? First, all the Kepler's law of planetary motion, then its explanation in detail. Okay, what are they called as? Law of orbits, law of areas, and law of periods. These are the Kepler's law that we will study.
Of periods. In the early 16th century, Kepler studied the shortcomings of Copernican model using the data gathered by his teacher, Tycho Brahe. Kepler concluded that all the planets revolve around the Sun in orbits, which were elongated rather than perfect circles.
Okay, what was the first thing that he informed? That the planets that are revolving around the Sun are not revolving in perfect circles. They are actually revolving as an elongated orbits. Okay, like means an elliptical orbit.
Based on his observations, Kepler propounded 3 laws of planetary motion, known as Kepler's laws. Kepler's 3 laws of planetary motion are the law of orbits, the law of areas, and the law of periods. Let's look at each law.
What are the 3 laws called as? Kepler's first law is called as the law of orbits, then the law of areas, and third one is the law of periods.
One by one. Kepler's first law, the law of orbits, states that the orbit of a planet is an ellipse with the sun at one of the foci. An ellipse is a closed, curved-shaped
Okay, this is the first law. You have to learn these laws. Okay, you can also refer your notes after seeing the video. Learn the topics from your notes, students. The orbit of a planet is an ellipse with the sun at the one of its foci. Okay, ellipse is a figure which has two focus. Okay, F1 and F2. But sun is available at one focus and planets are revolving around it in the shape of an ellipse. Okay, this shape that has been drawn is an ellipse.
At one of the foci.
You now see what is an ellipse? It is an closed curved shape that is defined by two foci. Okay, that means it is an elongated circle.
An ellipse is a closed, curved shape that is defined by 2 points, called foci, representing an elongated circle.
Like student, circle has only one radius. Circle has only one center with which we can draw a circle. Likewise, ellipse has two foci, F1 and F2.
The sum of the distance from a given point on the ellipse to the foci is always constant.
That means if we calculate distance from a point, okay, if I am taking this point, okay, it's distance from F1 and F2. In any other point, distance from F1 and F2, it will be always same. The sum of distances of any point from F1 and F2 would be same. Okay, the sum would be same.
In the given figure, A plus B is always constant. As you can see, in an elliptical orbit, the distance of the planets from the sun is not constant. The closest point on a planet's orbit from the sun is called perihelion.
Okay, we are seeing that the distance is different when the planet is moving. So that point which is closest to the sun is called as perihelion. You have to learn these terminologies, okay? We are seeing that here the distance is more, here it is more, here it is less. Then that point that is closest to the sun will be called as perihelion.
And the furthest point from the sun is called the aphelion.
Okay, and that point that is the farthest point from the sun is called as aphelion.
When a planet like Earth is far from the sun, the amount of heat reaching the Earth from the sun is relatively less. Hence, we experience a cold season. Conversely, when Earth is nearer the sun, we experience a hot season because more heat reaches the Earth. Kepler's second law of planetary motion.
Okay, this was the first law. Now let's see the second.
Also known as the law of areas, states that the line joining the planet to the sun sweeps out equal areas in equal intervals of time as the planet travels in its orbit.
Okay, this is the second law that you have to learn. The line joining the planet, okay, to the sun will always sweep in equal area, okay, at equal intervals of time. For example, I have taken time T1 and T2. Then area swept by it will be same if the other time intervals are taken, okay.
Let's explain this through an example of Earth's movements.
Okay, see it carefully. Now you can understand it better.
Suppose the Earth takes 1 month, that is 30 days, to travel from point P to Q on its orbit. Imaginary lines drawn from the sun.
Okay, what we are taking, we have taken time T1 and T2. That means a time interval of 30 days. Okay, if from P to Q Earth reaches in 30 days, then the red portion is the area covered
to points P and Q, together with the Earth's orbit, enclose a roughly triangular area. This area is equal to the area covered for any 30-day duration during the year.
Okay, now if we take the same duration 30 days, So between these also, this area and this area will be equal. That means this portion and this portion, the area would be equal. This is Kepler's second law, which is also called as law of areas. Why? Because the time interval is same. Okay, I am saying whether it is maths or it is science, you are getting the same marks. The subjects are different, but you are the same. Okay, that means you are bringing same marks in maths and science. Similarly, this earth is same, it is using the same time interval, 30 days. Here also 30 days, here also. So between any 2 points taking the same time interval, the area swept will be same. This is stated by Kepler's second law, that the line joining the planet to the sun sweeps out equal areas in equal intervals of time,
regardless of the Earth's position in its orbit. Thus, as shown, area A1 equals area A2. Further, according to Kepler, the speeds of planets in their orbits vary through the revolution around the Sun.
see these are.
When planets get closer to the Sun,
Closer, they are faster.
they move faster. Conversely, as they get further from the Sun, they move with relatively lower speeds. Therefore, the speed of a planet is highest at perihelion and slowest at aphelion. Kepler's third law, the law of periods, defines the relationship between the orbital period of a planet and the average radius of its orbit.
Okay, what is the third law? States that it is the law of periods. It tells the relation between orbital period and average radius. So first let's see what is orbital period and what is average radius.
Orbital period of a planet, denoted by T, is the time taken by the planet to make a complete revolution around the Sun along its orbit.
Okay, what is orbital period? That time taken by the planet to complete one revolution around the Sun, okay, along its orbit, is called as orbital period.
The average radius of the orbit of a planet is also the mean distance of the planet from the Sun.
What is the average radius? It is the mean distance of the planet from the Sun. Mean means average distance.
For example, suppose R1, R2, and so on are the distances of Earth from the Sun for n number of positions of Earth in its orbit. Then, the average radius of Earth's orbit can be calculated as shown. The law of periods states that the square of orbital period t of a planet is proportional to the cube of its mean distance r from the Sun.
Okay, this is your third law, that is the square of orbital period of a planet is proportional to the cube of mean distance from the Sun. Okay, t square is proportional to r cube. T is your orbital period and r is your average radius. This is your third law, that is called as law of periods.
Hence, you can express the law of periods as t square proportional to r cube, where t is the orbital period of the planet in Earth years, and r is the mean distance in astronomical units.
These are the units, okay, Earth years in astronomical units. Like for length we use meter, okay, like for temperature we use Celsius.
Astronomical unit, AU, is the mean distance between the Earth and the Sun. Thus, an astronomical unit is approximately 93 million miles or 150 million kilometers.
Okay, one astronomical unit, that means 1 AU is equal to 93 million miles or 150 million kilometers.
If we consider two planets, A and B.
What we are considering, students, we are considering two planets, okay, A and B. Then for A also, this this will be the relation. Okay, TA square will be proportional to RA square, and for B planet, TB square will be proportional to RB square. If we take their ratio, we will get this.
Compare their mean distances from the Sun and orbital periods. We get the relationship as TA square divided by TB square is equal to RAQ divided by RBQ, where TA is equal to orbital period of planet A. TB is equal to orbital period of planet B. RA is equal to mean distance of planet A from the Sun. And RB is equal to mean distance of planet B from the Sun. Scientists use Kepler's laws to determine the positions and the orbital periods of various planets in the solar system.
Okay, so these Kepler's law are very widely used to calculate the necessary information about the planets.
These laws also help us in calculations involved in determining orbital periods of satellites, natural as well as artificial. This brings us to the end.
Okay, so this was your first module. Today learn all these 3 laws and all the topics that we have discussed, okay?